Suppose you have 4 possible toppings for a pizza: mushrooms, salami, peppers, and olives. And you want to make a 3-topping pizza. Okay? So you have 4 toppings and you're going to choose 3 among them. How many different ways could you make a pizza? Pause the video and see if you can figure out how many different ways you could make a pizza with 3 toppings. Did you get 4? Here they are. Basically, you're just seeing how many ways could you leave out one topping. So you could leave out the olives, get MSP, leave out the peppers, get MSO, leave out the salami, get MPO, or leave out the mushrooms, get SPO. Okay, here's another one. Let's suppose now that you have mushrooms, salami, peppers, olives, and anchovies. And you want to see how many ways out of these 5 toppings could you choose 3? This one's a little trickier. Pause the video and see how many different pizzas with 3 toppings you could get. Did you get 10? Here they are. Now later on in the course, we're going to go through different techniques for actually coming up with these. Don't worry too much about it right now. But I want to give you this introduction to choosing things because it's going to come in very handy in a rather unique way, as you're soon going to see. Okay, 2 more questions for you. Let's suppose we have the 5 toppings, and out of those 5 toppings, we want to choose 4 for our pizza. How many different pizzas could we make? Pause the video. Did you get 5? This is like the first one again, because essentially we're just seeing how many different ways could we make a pizza where we're missing one ingredient, and the answer is 5. Okay, last question. Suppose you have 5 toppings to choose from. You have the 5. You're going to choose one single topping. You want a 1-topping pizza. How many different pizzas could you make? Pause the video. You should get 5. This is essentially the opposite of the previous question, in that here we're just saying, okay, out of these 5 different toppings, how many different single choices we could make. Whereas before, with out of the 5, how many 4-topping pizzas could we make, we're actually saying out of the 5, how many ways could we leave out one. So choosing a 1-topping pizza, when you have 5 choices, there's 5 different ways to do that. And choosing a 4-topping pizza, when there's 5 different choices, there are also 5 different ways to do that. Okay, so you're probably thinking, well, what does this have to do with arithmetic and geometric sequences and series and patterns and all the stuff we've been doing so far? Well, take a look at this pattern here. I'm going to start off with 1, and then I'm going to put a 1 just to the left and another 1 just to the right of the first one. And then I'm going to put another 1 just to the left and another 1 just to the right. But this time, as I come inwards, I'm going to add the 2 previous terms. So 1 plus 1 is 2. Okay. Then I'm going to put a 1 just to the left and a 1 just to the right. And then I'm going to add 1 and 2 to get 3, which I put here. And I'm going to add 2 and 1 to get 3, which I put here. Again, I'm going to put a 1 to the left and a 1 to the right. And I'm going to continue building this pattern. Here I would get a 4 because 1 plus 3 is 4. Here I would get a 6 because 3 plus 3 is 6. And here I would get a 4 because 3 plus 1 is 4. Okay, maybe I'll go 1 more down. This would give me a 5. This would give me a 10. This would give me a 10. This would give me a 5. And I have my 1 here. Okay? This is popularly known as Pascal's triangle. And it has an enormous number of very interesting applications and connections to other areas of mathematics. So I'm going to erase the arrows and clean this up a little bit. That looks better. All right. Now this is, in fact, a recursive pattern. In fact, it's a sequence of sequences. Watch how I number it. So this first row, I'm going to call this row 0 instead of row 1. Okay, so that's row 0. Row 1 will be here, row 2 is here, and so on. Okay, so that's the first thing. And then I'm going to take diagonal columns and count them off as well. So this column here is going to be the 0th column, column 0. This column here is going to be column 1. This column here is going to be column 2. This column here is column 3, and so on. Column 4, column 5. And the pattern, of course, could continue on, well, forever. Okay? So these columns continue to expand as we go down. And so do the rows, of course. All right. So now that I've got the rows and the columns set up, take a look at this. I can use recursion to define Pascal's triangle. So I'm going to start by defining U 0, 0, 0th row, 0th column, as 1. Okay, that's at the head of the triangle right there. U 0, 0 is 1. And then I'm going to say U I 0, ith row, 0th column, that's all of these ones here, will also be 1 for all values of I. Okay, no matter what I is, if it's the 0th column, the value is 1. And then I'm going to say, okay, also UII is 1 for all values of I. So this is where the row and the column are the same. That's all of these ones here. For example, this guy right here is in column 4 and row 4. So the column and the row are the same. His value is 1. Column 5, row 5, this one also 1. Okay, so far I've just set up my constants, and they're all 1. And then I say U, I, J, where I is the row and J is the column, is equal to U, I minus 1, here maybe I'll put a comma between my subscripts, I minus 1, comma, J, plus U, I minus 1, comma, J plus 1. What does this say? Well, it says, this is for all I and J, it says that to calculate the ijth term, what I do is I go 1 row up. So let's take, for example, this one here in row 5. So I equals 5. And column 2, so J equals 2. It says, look, go up 1 row and keep the same column. So that would be, you know what? I think I have a mistake. Hold on 1 sec. Okay, sorry about that. So the formula should actually be U I minus 1 J minus 1 plus U I minus 1 J. Okay, so this says if I have this term, go up 1 row and go left 1 column. So that would be here, plus go up 1 row but keep the column. So that would be here. Adding these two terms together is how I get this 10. That's the definition of how I am to proceed to get terms. Try it again for this one here, for example. We're at I equals 6, J equals 4. The formula says go to term I minus 1, so that would be 5, comma, J minus 1, so that would be 3. In other words, up 1 row, back 1 column to here. Add that to I minus 1, so that would be 5, and j itself, keep the column. So up one row, but keep the column, that would be here. Add those together, and you get this term. Okay, so Pascal's triangle is, in fact, definable using recursion. It's a rather complex pattern. All right, great. Well, that's kind of cool, but now you're thinking, okay, well, what does this have to do with pizza toppings? Well, let me show you. So suppose you're making a pizza, all right? And you have 5 toppings to choose from. And, well, to start with, you're going to make a very boring pizza. You're going to choose 0 toppings. How many different ways could that be done? Well, obviously just one. There's only one way to make a pizza with no toppings at all. Boring. Okay, how about if you have 5 toppings to choose from and you choose 1? How many different pizzas could you get? Well, you could get 5 different pizzas. You could have the first topping or the second topping or the third or the fourth or the fifth, just like we had right up here. Okay? Okay, now let's move along. Let's suppose now you have 5 toppings and you want to choose 2. How many different ways could this be done? Pause the video and see if you could figure it out. Did you get 10? Here, I'm going to just call the toppings A, B, C, D, and E for simplicity, and I just go through systematically. A, B is 1, A, C is the next, A, D is the next, A, E is the next, B, C is the next, because I'm done with A, B, D, B, E. Next, C, D, C, E, and last, D, E. There we are, 10 possible toppings. Next question, suppose you have a pizza and you have 5 toppings to choose from and you want to choose 3. How many different ways could you do that? Well, in fact, I'm going to save a little time. The answer is 10. Next, you have a 5 toppings to choose from and you want to choose 4. How many different ways could you do that? Well, this is the same as how many different ways could you choose to leave one out? The answer to that is 5. And lastly, we have 5 toppings. How many ways could we choose to have all 5 toppings on the pizza? How many different possible pizzas is that? Well, just one. The one pizza that has all 5 toppings. Okay, so we've got our pizza problem here, and we've got Pascal's triangle here. Can you see a connection? Have a little look. Look at this row right here. Notice anything there? That row contains the answers to all of these choosing problems. That's pretty phenomenal. Moreover, this 5, the 5 toppings that we started with, is the row number of Pascal's triangle, as long as we name the rows the way I did, starting with row 0 at the top. And not only that, but the number of toppings that we choose for our pizza is the column number, as long as we name the columns the way I did, with the first column being 0. 1, 1, 2, 2, 3, 3, and so on. Okay, so this is really, really, really cool, and it's amazing in so many different ways. And to be honest, we haven't even scratched the surface yet. This is just the beginning of Pascal's triangle and making choices, and we haven't even got into the binomial theorem yet, which we're getting there. This is really cool stuff. Now, one thing I want to point out is this means then that if you want, here, I'm going to get rid of this recursive formula. You don't need to memorize the recursive formula. I'm just showing you that Pascal's triangle is a special type of recursion. Let's suppose now that you wanted to know n, you have n toppings, and you're going to choose r. Or other notations, by the way, are n choose r. or n choose r. Okay, those three are equivalent. So suppose you have n and you want to choose r among them. All you have to do is go to the nth row, rth column of Pascal's triangle, and you have the answer to this. That can be very handy. This Pascal's triangle can be a very quick way to compute certain n choose r values. Okay, so for example, let's suppose I wanted to know 6 choose 4. I just go to row 6, column 4. The answer is 15. Now, before I go too far with this, I also want to show you that there's a formula for calculating n choose r as well. And it goes like this. If you have n choose r, that is equal to n factorial divided by r factorial times n minus r factorial. What's a factorial, you may ask? A factorial is a repeated multiplication starting with the number that is applied to the factorial and counting down to 1. So for example, if I have 5 factorial, that is equal to 5 times 4 times 3 times 2 times 1, which is equal to, gosh, that's 20, 60, 120. 3 factorial, on the other hand, is starting at 3. It's 3 times 2 times 1. That's just 6. 1 factorial is just 1. And 0 factorial is defined as 1. And there are a lot of very, very, very good reasons for that, which I'm not going to go into here. But that's something you need to know. Kind of like how a to the 0 equals 1. 0 factorial equals 1. Okay, so coming back up here, if I had 6 choose 4, yes, the answer is 15, and I can get that from Pascal's triangle, but I can also get it by using the formula. So if I had 6 choose 4, this is 6 factorial, n factorial, over 4 factorial, r factorial, times n minus r factorial. Whoops, I forgot to just make that a 6 minus 4. 6 minus 4 factorial. Okay, so this is 6 factorial over 4 factorial, 2 factorial. And in practice, the easiest way to calculate this, if you don't have a calculator, of course, is to say, look, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And I would not normally actually write them all out. 4 factorial is 4 times 3 times 2 times 1. And again, I would not write them out. And 2 factorial is 2 times 1. What I get is all of these canceling with all of those. So I'm left with 30 divided by 2, 15. Sure enough, 15, what we were expecting for Pascal's triangle. But also notice this canceling technique. Very, very helpful. If I had 5 choose 2, that would be 5 factorial over 2 factorial times 5 minus 2 factorial. I take the bigger of these, that's the 3. So I know up here, I basically have 5 times 4 times 3 times 2 times 1, but that 3 times 2 times 1 is going to cancel with the 3 factorial. So I'm left with 20 over 2, which is 10. Or in Pascal's triangle, row 5, column 2, there it is, 10. All right. So we've looked a little bit at choosing pizza toppings, how many different ways we can get a pizza with a certain number of toppings when we have a certain number of choices. We've looked at Pascal's triangle. We've looked at how to generate it by adding numbers to generate those that are below. We looked at the connection between Pascal's triangle and n choose r. And we've looked at the definition of n choose r with the factorials and how to compute it. What next? Well, look at this. So there's actually another connection. Let me take, for example, x plus y, to the n. Okay, we're going to calculate x plus y to the n for n starting at 0, going to 1, 2, 3, 4, and so on. Why don't you go ahead and calculate x plus y to the 0, x plus y to the 1, x plus y squared, and maybe also x plus y cubed, and see what you come up with. Pause the video and try that out. So here are the first three. Anything to the exponent of 0 is 1. So x plus y to the 0 is just 1. Anything to the exponent of 1 is itself. So x plus y to the 1 is just x plus y. X plus y squared means x plus y times x plus y. Don't forget to write these binomials out in FOIL. You cannot say that this is just x squared plus y squared. That is wrong. Okay, so once I have my binomials written out and I FOIL, I get x squared plus xy plus xy plus y squared, and collecting like terms, I get x squared plus 2xy plus y squared. Now let's do x plus y cubed. Well, first of all, this is x plus y times x plus y times x plus y. And x plus y times x plus y, we just did that. That's x squared plus 2xy plus y squared. Now I have to multiply this binomial by this trinomial. So x times x squared is x cubed, x times 2xy is 2x squared y, x times y squared is xy squared, y times x squared is x squared y times 2xy is 2xy squared, y times y squared is y cubed. Collect like terms. Now notice when I did this, I lined up my like terms. These are like terms, these are like terms. That makes it easier for me to add my like terms, right? So when I took my x and multiplied it by my x squared, I put that here. X times 2xy, I moved over 1. X times y squared, I moved over 1. But then when I came over to the y times x squared, that being x squared y, I lined it up with the other x squared y. And then the next term, I lined it up. And the last one got its own spot. Okay, so I'm going to add these up to collect my like terms. And what do I get? Well, I get x cubed plus 3x squared y plus 3xy squared plus y cubed. All right, let's do one more. I'm going to do x plus y to the fourth. Okay, here we go. So here we have it. X plus y to the fourth is x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. If you want, you can pause the video and go through this multiplication. What I did here was, to make this multiplication easier, I wrote right here the answer to x plus y squared, and then again x plus y squared, and multiplied those together. That was less work than if I had done it piece by piece. All right. Now, what do you notice here? Looking at all of these. Well, let me make this a little bit more clear. Let me take, I'll take this reddish color. I'm going to get my coefficients. So here we have just a 1. Here we have 1x and 1y. Here we have 1x squared, 2xy's, and 1y squared. Is this starting to form any sort of pattern that you recognize? How about the next one? I'm going to get 1x cubed, 3x squared y, 3xy squared, 1y cubed. What have we got so far? So the first one was a 1, then we had a 1 and a 1, then we had a 1, 2, and a 1, and now we have a 1, 3, 3, and a 1. What the heck is this? Can you believe it? Look at this. X plus y to the fourth. I have a 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. What the heck is this? If you take a binomial, x plus y, and you raise it to the exponent of n, the coefficients of your terms come from Pascal's triangle. How cool is that? It's incredible. And not only that, here we just have a 1 when n is 0. And remember how I named the rows? This is row 0. Here is row 1 when n is 1. Look, we get those two 1s. When n is 2, we get 1, 2, 1. Well, I named this row 2. Row 3 gives me the coefficients for when n is 3. How do you like that? This is really, really cool. And as I tell you, it doesn't stop there. But we're going to stop there pretty soon. Pretty shortly, we'll have done enough for our lesson for today. Okay? We've got these really amazing connections between Pascal's triangle, n choose r, and binomial expansion. Okay? And so now let me use this, and I'll do a few examples, and we'll go from there. So first of all, what does this mean in terms of binomial expansions? For example, if I have x plus y to the 5, okay, and I've got to expand this thing, I am not going to do it the way that I did it up here, right? I'm not going to go through this work. I'm just going to go over to the side, make a quick Pascal's triangle. I'm going to come down to row 5, 0, 1, 2, 3, 4, 5. And I'm going to read off my coefficients. This is going to be 1 x to the 5th plus 5 x to the 4 y. Okay, the exponent on the x goes down by 1. The exponent on the y, which here is 0, goes up by 1 to 1, plus 10 x cubed y squared plus 10 x squared y cubed plus 5 x y to the 4th plus 1 y to the 5th. See how easy that is? Beautiful. Okay, if I needed to do x plus y to the 8th, it's really not that much more work to fill out that Pascal's triangle and do it. The exponents on the x's start at n and go down by 1 each term, all the way down to here where the exponent is a 0, and anything to the 0 is 1, so we don't normally write it. The exponents on the y's start at 0, okay, so I don't normally write that, and then they go up by 1. Y to the 1, 2, 3, 4, 5, okay? And the coefficients match Pascal's triangle. How cool is that? Okay, let's do another question here. Let's suppose that I want to know... Oh, hold up. I forgot to even tell you. Right. So, I mean, I just told you in words, but let me lay this out here. If we have x plus y to the n, we know that this is Pascal's triangle for the coefficients, right? But we also know that Pascal's triangle gives us n choose r, right? If I'm here, for example, that is 0, 1, 2, 3, 4th row, 0, 1, first column. This is 4 choose 1. And if we wanted to, we could make an entire Pascal's triangle just with choose notation, right? Now, I mean, it looks kind of funny because I don't have any values, but this here, this Pascal's triangle, every single element maps over to a choose question, okay? So all of these map over. If I'm going to put another one in here and another one over here, just to fill it out a little bit, this would be 2 choose 1 and 2 choose 2. So 2 choose 1 is 2, and I could go through for the whole thing. So what does this mean in terms of binomials? Well, it means that we can expand a binomial in terms of choose notation. This is n choose 0, x to the n, y to the 0 if you will, plus n choose 1, x to the n minus 1, y to the 1, plus n choose 2, x to the n minus 2, y to the 2, plus, you see the pattern? N choose 3, x to the n minus 3, y to the 3, plus, and it goes on and on and on and on and on, all the way until we're at n choose, let's say we're at n minus 1, we're almost at the end, second last term. N to the, well, the second last term would be 1, and y to the n minus 1. And the last one would be n choose n, which is 1, x to the 0, y to the n. How about that? This is called a binomial expansion. We've got a binomial raised to an exponent, and we are going to expand that. And here we have it in choose notation. That's pretty incredible. And you know what? I'm going to take this another step further. We can write this in summation notation. Now, a few of you out there might be cringing a little bit, but take care. Go slowly. It's not so bad. All of the coefficients are a choose notation, and they all start with n. What changes? Well, what changes is the r value. It starts at 0 and it goes up 1 by 1 by 1 by 1 by 1. Okay? So I'm going to call this, now I want to be consistent here. Let me look for a second. I'm going to call this k. Okay? And I'm going to go from k equals 0 up to n. So when k is 0, this is n choose 0. That matches our first coefficient. When k is 1, we get n choose 1. That matches our second coefficient. So far, so good. Now I'm going to take n x to the n, but I'm going to subtract off k. So that when k is 0, we're not subtracting off anything. We get x to the n, as we would expect. When k is 1, we get x to the n minus 1, as we would expect. All the way to when k is n, the last term, we get n minus n, which is 0, as we would expect. And we'll have y to the k. Okay, so y starts with an exponent of 0 when k is 0. Then k goes to 1, we get y to the 1. K goes to 2, we get y to the 2. All the way to the very end, k is n, we get y to the n. Okay, so this here is a nice compact notation for a binomial expansion. Okay, this is actually, once you get on in university, this is considered the way that we would normally write the binomial expansion formula. A super, super important formula. Okay. So this is all good. Okay. But I want to call your attention to something in particular. Okay. And this is definitely worth memorizing. I want to call your attention to the fact that in particular, the kth term in a binomial expansion is n choose k minus 1, x to the n minus k minus 1, y to the k minus 1. Now, we have to be careful here. I have k minus 1 everywhere. Why do I have k minus 1 everywhere? I have k minus 1 everywhere because if I have for example, x plus y squared, and I get x squared plus 2xy plus y squared. This here is the first term. And earlier, we were calling this the 0th column. The coefficient here was the 0th column of Pascal's triangle, right? This was the 0th column where the 1 comes in. But now I'm saying, hey, no, this isn't 0th, this is the first term. So to compensate for that, so that we can truly call this the first term, this the second term, and this the third term, I am shifting in this formula the k to a k minus 1. In other words, when I'm on the first term, I have 1 minus 1, I'm going to get a 0, just like I would expect here. And I have 1 minus 1, n minus 0, just like I would expect here, okay? So this is just a way to map this so that I can call this the first term and the formula works. Very, very useful formula. You will want to memorize that one for sure. Okay. So this covers all the theory of the binomial theorem for now. This covers what you need to know for exercises 1N and 1O. However, I'm going to make one more video in which I talk about how to use the graphing calculator to quickly calculate n choose r, and where I do some examples involving Pascal's triangle, binomial expansions, and that kind of thing.